A 1-ton carbon fiber sled hovers over a cold steel rail, silent, floating, surrounded by hundreds of lethal neodymium magnets. In just 5.3 seconds, a massive electrical shockwave rips through the floor and launches this vehicle to 800 kilometers per hour. This frictionless magnetic corridor is completely lethal. Walk in wearing steel, and the magnetic pole turns your tools into shrapnel. At these speeds, if the concrete track shifts by even the width of a human hair, the entire vehicle disintegrates instantly. Launching this machine takes the electrical equivalent of a lightning strike. Nearby substations physically hum from the surge. Yet inside this aerodynamic shell, no seats, no windows, no life support of any kind. An emergency stop slams the chassis with 25 Gs of deceleration, a force that crushes human organs on contact. It's officially one of the fastest ground vehicles ever built. It punches through solid air, sending shockwaves rattling across the entire facility. So why did engineers spend billions building an 800 kilometers per hour machine that no human could ever survive riding? Every bullet train on Earth is quietly destroying itself the moment it crosses 300 kilometers per hour. At extreme speed, steel wheels don't just wear down, they disintegrate into molten fragments from pure friction. Friction is the enemy of ground transport. But past 500 kilometers per hour, the track isn't what kills you. The air itself compresses ahead of the nose, hardening into a dense, invisible wall of force. Standard high-speed trains burn over 80% of their energy just fighting atmospheric drag. Double the speed, and drag doesn't just double, it multiplies 4 times over. Motors overheat, power lines snap from vibration, efficiency collapses. At 800 kilometers per hour, faster than a commercial jetliner, open-air rail simply stops being physically possible. The displaced atmosphere creates a localized sonic boom, capable of tearing panels straight off the frame. To break this wall, engineers had to tear up the rule book of railway design and start from zero. Beating friction was only half the fight. Human biology was the far deadlier obstacle. The human body simply cannot survive the acceleration required for a ground launch at these speeds. At 25 Gs, blood is forced out of the brain in an instant. Blackout, stroke, or fatal organ failure follow. Emergency braking inside a sealed tube generates deceleration violent enough to snap a human neck. And running inside a near-vacuum tube means any microscopic hull breach triggers explosive decompression. In that near-zero pressure, human lungs collapse within seconds. There's no time to react. A jet can drop altitude and deploy oxygen masks. An underground steel tube offers no air at all. A single thermal fault or magnetic drop at these speeds turns the cabin into a pressure cooker instantly. The engineering verdict was blunt. Right now, a passenger cabin violates the limits of human survival. If China wanted near supersonic ground speed, humans had to be removed from the equation entirely. The breakthrough meant fusing 2 extremes: superconducting levitation and total atmospheric removal. Step 1. Eliminate physical contact completely by floating the chassis on a continuous magnetic cushion. Step 2. Seal the track in an airtight concrete shell and pump out 99% of the air inside. With no atmosphere to fight, drag drops near zero. Incredible speed on a fraction of the power. A single magnetic pulse can sling a multi-ton sled to fighter jet speed without burning a drop of fuel. China Aerospace Science and Industry Corporation led the project, codename T-Flight. Instead of a luxury passenger line, the priority was automated logistics, aerospace testing, and military payloads. This wasn't civil infrastructure anymore. It was aerospace technology built flat on the ground. Pull the air out of the tunnel, lead researchers said, and the Earth becomes an open runway. The physics worked in simulation. Building it for real would take pure mechanical violence. In Shaanxi province, excavators ripped open the earth, stripping topsoil down to solid bedrock. Over 500 concrete piles were driven into limestone bedrock to guarantee zero soil settlement. At 800 kilometers per hour, a ground shift of half a millimeter hits like a concrete wall. Satellite-guided lasers measured every centimeter of the corridor before a single bolt went in. Concrete caps were hand-ground until perfectly flat, the foundation for immense structural loads. When 3 support columns drifted by a hair's width, hydraulic jacks forced the multi-ton blocks back into line. Engineers swapped steel rebar for carbon fiber tendons. Steel expands in heat, carbon doesn't. 40-ton concrete beams moved only at night to stop sunlight from warping them. Cranes set 50 beams with satellite precision across 3 straight months of night shifts. Every joint was hand-finished in zero-shrinkage aerospace concrete, a foundation built for violent shocks. With the foundation locked to bedrock, crews lowered 200 concrete roof sections over the track. Each 12-ton arc was polished glass smooth inside to prevent deadly turbulence at speed. Custom rubber seals went into every joint in brutal heat to keep the vacuum airtight. This isn't just a train track. It's a 1-kilometer linear particle accelerator built into the countryside. Industrial pumps ran for hours, draining millions of liters of air from the tube. Robotic arms laid 2,000 propulsion coils into the concrete bed using aerospace-grade adhesive. Every coil was scanned for air gaps. Trapped air becomes plasma arcs under high voltage. Precision grinders shaved the steel rails section by section until the surface was flawless. Substations were wired with over 4,000 power cables, 8 straight months of electrical work. The track was fully armed and sealed, ready to channel 40 tons of power in a split second. The sled rests on a propulsion floor built from 28 hand-laid layers of carbon fiber. Over 300 neodymium magnets line the underside, generating 800 kilonewtons of repulsive force. Drive units generate a traveling magnetic wave along the floor, locking the sled into an invisible current. If a single stator winding is off by just 2%, the magnetic wave collapses instantly. The sled would drop at full speed, grinding into the concrete in a wall of fire. Thick copper heat sinks absorb the intense thermal load to stop magnetic decay. Lateral guidance magnets lock the sled dead center, killing any destructive side-to-side wobble. Over 100 wireless sensors stream live telemetry back to the control bunker. Engineers balance the sled's ballast with extreme care. A tiny offset creates fatal oscillation at speed. The nose cone is built with sacrificial crush zones, designed to fail safely in an emergency. Workers use only non-magnetic aluminum tools. Steel wrenches would be ripped away as lethal projectiles. Inside the Datong control bunker, klaxons sound as 800 supercapacitors finish overnight charging. The tunnel is cleared, sealed airtight, and pumped down to near vacuum. Substation transformers hum with 50 megawatts of stored energy, ready to fire in 5 seconds. Countdown hits 0. The system dumps 40 tons of raw power straight into the coils. The sled detonates forward at 25 Gs, a missile launch down a silent corridor. Telemetry spikes as speed climbs from 200 to 600 kilometers per hour in 3 seconds flat. Inside the tube, compressed air forms a visible shockwave slamming against the walls. At exactly 5.3 seconds, The sled crosses 800 kilometers per hour, a new ground speed record. The track reverses polarity instantly, slamming the sled into a frictionless magnetic wall. In under 200 meters, the sled comes to a complete stop. Zero brake wear. Thermal scans confirm the ceramic nose and carbon frame are fully intact. Ground-based hypersonic transit is real. 50 consecutive record runs later, the sled's mounting brackets reveal the real purpose. This was never just cargo infrastructure. It's an electromagnetic launch system. Mount a military drone to this sled, and it hits 300 kilometers per hour in seconds, airborne before it clears the tube. Instead of burning thousands of gallons of jet fuel on takeoff, the rail catapults the aircraft into flight. Lead engineers confirmed the same system supports horizontal launch tech for rockets and defense payloads. Slingshotting a rocket horizontally through a vacuum saves massive amounts of onboard propellant. A parallel defense test hits 700 kilometers per hour in 2 seconds. Classified aerospace prototypes only. Swap the cargo sled for a reconnaissance drone, and the same track becomes a weapons launcher in minutes. While Western Hyperloop projects stalled on funding, China's military-backed facility just delivered results. This was never a failed passenger experiment. It's a ground-based aircraft carrier. Construction is already extending the Shaanxi track. The next target is 1,000 kilometers per hour. At that speed, a ground vehicle outruns a commercial airliner, linking megacities in under 30 minutes. A national network would bypass air traffic entirely, moving high-value freight at aerospace speed. Passenger travel means redesigning the entire launch profile to keep G-forces survivable. Cabins will need fighter jet-grade pressurization and advanced dampening systems. The foundation is set. We're watching the birth of ground transport that finally rivals flight. And it all started on a 1-kilometer track in Shaanxi. Proof that to fly across the Earth, you first have to master the violence of empty space.